Wow, I'm definitely getting a white cube anxiety. It's very white. White or not, I hope you guys are enjoying the Lunar New Year holiday. And before we get started, I just want to wish you and your family and your loved ones a wonderful year ahead. I hope 2025 brings nothing but joy and amazing things to you, incredible human beings. So let's get started on exponential function. From our activity that we did using our Skittles to model the cancer's cell growth last week in class, you guys probably already noticed that this thing called exponential function is very different from the other types of functions that we are used to seeing. One big comparison we can draw is comparing exponential function to something like a linear function. So let's take a linear function, for example, like function of x equals 2x. As our input values change, the y values increase by double. By y values, I mean function of x, our output. And if you take a look, I know that this is kind of growing at a very steady pace, and we call this constant rate, right? So this function increases at a constant rate, giving it a nice straight line, and there's no y-intercept, just FYI, or I should say my y-intercept is 0, so therefore this is a very typical, simple, direct variation. Okay, so now let's take a look at an example of an exponential function then. We have another function of x, but this time we have 2 as our base, and that is raised to the power of x. So this is very different from the radical functions we looked at in our previous chapter, where our x serves as the base and we have a constant fixed exponent. In the case of an exponential function, we have a fixed base and our input simply fluctuates. So again, I'm gonna go ahead, make a simple table with the same values of x that I used for the linear function. And what do we see? We see that when x is 0, y is 1. When x is 1, y is 2. And x is 2, y is 4. When x is 3, y is 8. And when x is 4, y is 16. So as you can see, my linear function is nice, steady line, and my slope is 2. And if you take a look at my exponential function, even if you're not familiar with the graph of an exponential function, what you can see is that actually in comparison to the linear function, our graph starts out a little bit slower. It's not increasing as dramatically in the beginning, but soon, if you take a look, the gap is huge, right? It shoots up. That's why we'd say it increases exponentially, right? Before we go into like the useful application of exponential growth, I want us to take a look at some of ways we could apply transformation to exponential function. We're going to continue to work with y equals 2 raised to the power of x, and this is going to serve as sort of the basis. So this is going to be our parent function, our OG function, right? So this time around, since just now we went ahead and looked at the values of y when x are 0, 1, 2, and 3, I want to start out with negative values. So when x is negative 2, y would be 2 raised to the power of negative 2, which would give me 1/4. And when x is negative 1, I have half. And 0 and 1 and 2, we know that very straightforward. So let's go ahead, plot these. And if you take a look at our domain, remember domain is all the possible values of x for this particular function. What we'll notice is that we could literally plug in any sort of real number, right? So our domain is negative infinity to positive infinity. However, when it comes to range, we have to be careful, because let's think about it. Let's imagine that we are raising 2 by negative 100. What would happen? Would my y value be negative? No, it would simply be 1 over 2 raised to the power of 100, which is teeny tiny number, right? Very, very close to 0. So that tells me is that as my x values get close to negative infinity, means they get infinitely small, what I'm going to notice is that y value would get super duper really, really, really close to 0, but we would never reach 0. Think about it. If y equals 0, can you give me any value of x that we could put in? No, because even if x was 0, y would be 1. And if x was anything negative, it would just give us a fraction that's in between 0 and 1, right? So my range is 0 to infinity. Now, let's go ahead and add 2 to my exponential function. So I have over here y equals 2 raised to the power of x plus 2. I'm going to go ahead, take the same values of x, and make another set of table. And once I plot them right on top of the blue graph that I have, which is a parent function, what I'm noticing is that we literally took that blue function, blue graph, and we simply moved it up vertically. That means moving it up by 2. So it has vertical shift by positive 2 units, right? And that makes sense, because if you compare just y values, all the y values from our parent function, we take them, we add 2 to them, and that's what I get for the function written in fuchsia. That's the color. So what if I then add 2 to x, to that exponent, our ever-changing exponent? Again, I'm going to take the same exact values and create this table. And what I notice is that this time, actually, the entire graph, again, the blue graph, which is a parent function, is shifted not by positive 2 units, so not in the right direction, but to the left, towards the negative. And that's because if you think about it, I'm sorry. Remember, in our original OG function, 2 raised to the power of 0 gave us 1, right? But now that I have x plus 2, x would have to be negative 2 in order for y to give us the same exact value of 1, correct? So therefore, what was once at 0, 1 coordinate point would now have to shift to negative 2, 1, correct? So just like that one coordinate point that had to get shifted, everything else on the original parent function got shifted by negative 2 units. All right, this time we're going to take a look at how multiplication affects our exponential function. So first, I'm going to start out with multiplying half to my exponential function, y equals 2x. Y equals 2 raised to the power of x. So if I were to create a simple table, this time I only have 3 values. I have x equals 0, x equals 1, x equals 2, and I go ahead and plot the points. What I notice is that our original parent function is in fuchsia. and take a look at my blue graph. My blue graph is actually kind of like, it's almost like it's ready for a nap, right? So it's almost like somebody took, somebody like pressed the graph down, the original graph down, correct? And we call this vertical shrink. So if you compare our original values of x and y to this new set of values of x and y, what I would notice is that for the same values of x, my y values are exactly half, correct? So we call this vertical shrink. Or we could also call this let's call that vertical shrink. Yeah, vertical shrink by half. And now, what if we multiply 2 instead of half to 2 raised to the power of x? Same thing, and what I notice is that this time my values of y are actually a lot bigger. They're double my original values, right? So once I graph them, what I notice, as you can see in the red graph, is that it's almost like you take the original graph and then you stretched it, elongated it. So we call that vertical stretch. So my blue graph represents vertical shrink by half, like somebody pressed it down by half, and my red graph represents vertical stretch by 2. Okay, I think that's pretty straightforward, but what if we go ahead and multiply -1 to my exponential function? Once I do that, once again, I created a simple table, as you can see. What I'm going to notice is that in comparison to the parent function, it's actually identical, but simply reflected. It's reflected by my x-axis, correct? So